Okay. So today I'll start uh, with highlighting the main differences between the divide and conquer approach and dynamic programming approach. So we have seen both of this, quite a few examples of divide and conquers as well as dynamic programming also, right? And okay, apart from this, in our last class, what we did is in 0-1 knapsack, but in the tutorial class also, we looked into another problem, like longest common subsequence problem that we have also seen, right? Okay, okay. So, so what we did, so main difference, I'll highlight few uh, significant differences between divide and conquer approach and dynamic programming. So in divide and conquer, what we do is we generally go for the single way of dividing the input, right, into smaller and smaller subproblems. Like in merge sort, we always break it into half, right? But in divide and conquer, although we look into, so both of these problems are looking into some subproblems. And from the solution of the subproblems, both of these problems are trying to gather the solution of the original problem. Right? Now, what is happening in dynamic programming is it's not one way, so its solution can come from many different subproblems. For example, what I'm saying here is in this one, when you have this recurrence relation of 0-1 knapsack problem, its solution can come from this part. Also, it can come from this part. Okay? I don't know from which part the solution is coming. So I have to keep track of both of them. Right? But in contrast to that, for example, in binary search, what we do? Binary search is a dynamic programming. So depending on the middle element, I decide where my whether that element could be there in the array or not. So either it should be in the left part or it should be in the right part. So and then once I make that decision, I keep on recursing in one direction. That is in divide and conquer. Right? So once it comes to a single way of division and then it goes to the smaller and smaller subproblem. But whereas in dynamic programming, we have to we have to keep our options open so that solution can come from any of these subproblems, from this one also, from this one also. So let me write it down. So main difference in the way of in this approach is in divide and conquer. Divide and conquer commits to a single way of division. Right? So it's always gets a single way of division, and once it decides that, it keeps on doing that same division again and again, right? But in dynamic programming, I'll write it DP. In dynamic programming, we keep our options open. And that is because the optimal solution can come from any smaller subproblems, right? Another striking difference is that in divide and conquer, our subproblems are generally not overlapping, right? But it's quite frequently in dynamic programming, our subproblems are kind of overlapping subproblems. They are not always uh, different subproblems. That's why we are in dynamic programming. We are always interested in finding how many different subproblems are we solving. One subproblem can appear many times in the whole process, but we are actually solving it only once. Right? So in dynamic programming, subproblems are generally recur across uh, different recursive points. That is the reason why memorization helps. Right. So we are solving different subproblems, and subproblem can be like may require to solve many times. But what we do, we solve it only once and store the value in a memorization table. Right. That's the reason. So it's memorization helps. Right? But in divide and conquer, things are not like that. Subproblems are distinct subproblems. But in divide and conquer, subproblems are distinct. Right? So next, it's basically the way why to use these uh, techniques. Generally, this divide and conquer approach improves the running time. And okay. We have seen a few examples of this. So that's discussed in the tutorial class as well. Like so, uh, multiplication of two n-digit numbers, right? So how we do that? Our general way of multiplying things is not. I mean, it gives you. We have seen this. It gives n squared running time, right? But if we use a divide and conquer approach, that sometimes helps in developing improving the running time of this, right? So from that we get log of uh, log n to the power 3 by 2. Right? So that's the thing. So divide and conquer generally helps in improving the running time. But if a dynamic programming solves a problem in so problem in polynomial time, its straightforward implementation is generally exponential. So that we have seen again and again. So in generally, nth Fibonacci number takes exponential running time, but using memorization, we can bring the running time down to uh, something polynomial, right? And not polynomial. So it's 2 to the power n, and for after using divide and conquer, sorry, dynamic programming, we can bring it down to O of n. Right? And also like mm, we have seen this maximum non-consecutive sum example. That also in general we can solve it in exponential time. But by using divide and conquer, we can sorry, we by using dynamic programming, we can solve it in mn time, right? So longest common subsequence also we have seen, like we can do it in mn time. Right? In divide and conquer, subproblems are chosen to optimize the running time. So our intention is to how can we bring down the running time of that process. Right? That's what we said. Like generally helps in improving the running time. Divide and conquer generally helps you in improving the running time. So how we choose our subproblem accordingly to optimize the running time, and we don't like, need to think very much about the correctness of this. Correctness becomes easy. Correctness of the problem, it becomes easy. So this point, this fourth point is basically how to approach this divide and conquer and the dynamic program. So while designing a divide and conquer approach, our goal is to figure out how can we improve the running time of this. And that's the guiding force of choosing the subproblems. But in dynamic programming, our we first look into the solution of the original problem and then try to analyze it. And we design it in such a way that our correctness stays in our mind. So if that's the solution, how can this solution come from? Either it contains that element or doesn't contain that element, right? So correctness, we are designing our subproblem thinking of the correctness of the process itself, right? In dynamic programming, the subproblems are designed keeping correctness in mind. In mind, right? In divide and conquer, we try to get smaller subproblems whose size is a fraction of the bigger subproblem. Like, why is that? Why you are trying to always get to a subproblem whose size is kind of fraction of the original problem? Can anyone think of that? Yes. So divide and conquer approach. So as I said, like uh, just said in the previous point, our goal is to how to optimize the running time, right? And we have already discussed while discussing the running time analysis of divide and conquer approaches. It running time will be less if our subproblems are a fraction smaller than the subproblem, original problem, right? It's not constant time, constant. It's more. It's not smaller by a constant, smaller by a fraction. That's what we want. That is why we are trying to always get the subproblem to size a fraction of the bigger problem. But that's not the case in dynamic programming, right? That is not how we think of this dynamic. Okay. So these are mainly the differences that you should keep in mind, right? While designing, which one would you like to apply? So once you have to apply dynamic programming, first you have to come up with a solution, come up with a recurrent solution of the solution, right? And how to design that? You have to think, analyze the solution of the problem, and from that analysis, you have to figure out what are the subproblems, what are the possible subproblems. And once you get to that subproblem, uh, at that point you don't know your solution of the original problem is coming from which subproblem. So that's why you have to keep your options open. It can come from any of the subproblems, right? But in divide and conquer approach, so we know some algorithm for this. I want to optimize its running time. I can try for divide and conquer approach. And our main, so since that's our main objective, we try to figure out the subproblems whose size are fraction smaller than the original problem, right? Otherwise, it will not help me in helping in improving the running time. Okay. And once we make that decision that which are the subproblems, we are always going to keep dividing our problem in the same way. And in some cases, I can throw away the complete one part of it, or maybe more than few parts of it. That's how in divide and conquer, running time gets improved. Okay, fine. So, any question regarding these things? Okay, fine. So I guess there's no question. Okay. So now we're going to see another designing algorithm designing technique, and that technique we call it a greedy technique. So explain the second point. This one. Oh, this one is the main crucial point here. So uh, in divide and conquer, what we did. So we, for example, divide and conquer, as an example of a divide and conquer, it's you can think of binary search. Right? In binary search, what we do, we have a sorted array. We break that array into two equal parts based on the middle element. We compare the element that we are looking for. We compare it with the middle one, and then decide whether if that element is at all present in the array, then which part is it, right? And so what are the subproblems? So either that element should be in the left part or in the right part. These subproblems are distinct. Right? It's not, it can be in this part or left part also, it can be in the right part also. I have to look into that part. I also have to look into that part. It's not. But in DP, uh, what we do is we generally divide the problem into some smaller subproblems, and uh, we divide the problem into some smaller subproblems, right? And generally those subproblems can repeat in the whole process. It can repeat. Okay. And we don't solve those subproblems many times. We solve each different subproblem only once. And once I solve it, I store its value to some memorization table. Right? That's why it says, like the second point is saying, that it generally recurs across different recursive calls. This is the same subproblem. Right? And that's the reason why I can memorize and get a better running time. Okay. Is this second point clear now? Okay. And okay. So while explaining the second point again, so I have one question in my mind. Uh, it's kind of okay. So again, okay. Uh, okay. Maybe this question might help you in answering or understanding the second point. So I have a sorted array. I want to search for this element X, whether this X is there in the sorted array, in this array or not. Right? And this is one problem. Uh, in the right hand side, I'm also writing something similar problem. Uh, Search for this element X, but this time this array is not sorted. So you know how to solve this in the left problem. It's basically binary search, right? Now, can you tell me a divide and conquer approach for the problem in the right hand side when the array is not sorted? Can I use some divide and conquer approach? Divide and conquer. Can you think of a smaller subproblem of this? Again, I can think of breaking the array into two parts, left and no. Okay, so merge sort. I'm not sorting. Sorting it's a bigger problem. Sorting is significantly harder problem than searching. Searching is much easier. So if you are applying merge sort, you are actually overkilling it. So think about this approach. So I have unsorted array. I'm breaking it into equal parts, A and B. Right from this itself, this middle point itself, I'm breaking it into equal parts. Right, and then I search for X in both the left part and the right part recursively. Okay. Then can you tell me what would be the running time of this, or what would be the solution of the original problem? So if I get my answer to be no here, can I tell you what is the answer there? The other part. So to tell me the solution of this, when this would have a yes solution, can you think that yes solution of the original problem in terms of the solution of the left the smaller sub problems? Is this question clear? So when this original solution will be yes, this solution to this problem will be yes. Anyone? So it would be yes when either this or this has a yes answer. Either this has a yes answer or this one has a yes answer. So it's saying like X is present in the left part or X is present in the right part. Then only I can say that the solution of the original problem will be yes. Right? What is the other case? Like, so if I have no here and also no here, so then my answer will be no. That element is not present in this. Okay. This is kind of dynamic programming approach because you are dividing it into subproblems. That's okay. But you have to you have to keep your options open. Your solution may come from this solution of the left part or may come from the solution of the right part. But that was not the case in here in binary search. When you have left subarray. So when you are committing to solve the subproblem in the left hand side, then only from the solution of this, if this is yes, then you can tell this also has yes answer. And if this is no, then you can also tell this has no answer. You don't have to look into both the solutions of the subproblems, right? Okay, I hope this is clear now. Right. Okay. Okay, fine. So now, let me just what I was saying. I'm about to start another new problem, a new algorithm designing technique that we call it's called greedy technique. Right? I'm going to study this new technique, and the problem that I'm going to solve, it's again something that we have done. It's actually like done in the previous class itself. It's again, it would be the knapsack problem. But it's not the same knapsack problem, but we'll see uh, a variation of that knapsack problem. Okay, so just uh, quickly, I'll just copy. Yes, just okay. This was the problem of knapsack. Right. Now, mm, as I mentioned, this is called a 0-1 knapsack. Okay. But I will change it something slightly different and I'll name it fractional knapsack. Okay. Uh, so what is the difference? So this objective function I have to change, but the input remains the same. So I'll be giving you n items along with their values v1, v2, vn, and their sizes s1, s2, sn. Okay. And I'll also give you a knapsack whose capacity is capital C. Again, I have to put some items into my knapsack. Okay. And I have to keep filling my knapsack. And also I have to maximize the total value of the knapsack. Whatever item I am putting in my knapsack, that should have maximum value, right? But what is the difference between this fractional and the original one, 0-1 knapsack? The main difference here is that we are allowed to take some fraction of an item. Okay. So earlier it was not the case. Earlier it was 0, 1 knapsack. Right. Why is that 0, 1 knapsack? Means it can be either 0 or 1. Either I can take the whole item, whatever amount available, whatever size is there of that item, and then I have to take whatever value that contributes to. Okay. But this time I am allowed to take uh, I'm allowed to take some fraction of that item. So suppose if an item is having uh, size, let's say 10, right? So I can take in my knapsack, I'm allowed to take 5 unit of that. So if its size is 10, so I am allowed to take 5 unit of that item. Or in simple terms, you can assume that the items are kind of liquid items. You can take some amount of that. Is this clear? Okay. So then how can I write what would be the uh, output? What should I output? Earlier, recall that the output that we are taking, the output that we were reporting was which items I'm taking, some subset of the items 1 to n. Now this time I am not supposed to do that only. I have to tell something else. Wow, what are the items that I'm taking? And also in what fraction? Either we are taking it completely, or we are taking some fraction of it, or we are not taking it at all. Those things I have to tell. Okay. So how can I express that? Well, I will keep this aside. Uh, can you tell me how should I express my output? It output would be in some kind of a vector, right? Uh, some vectors where these xi's are lying in between 0 and 1. Okay, so this xi is representing fraction of the item taken. So for the first, so x1 is representing for the first item, I'm taking that fraction of it. So if it's, for example, if the size of this is 5, size of the item is 10, and I am taking 5 unit of it. So what is X1? X1 is basically half. I am taking half of that item. Okay. And for, I have to tell you for each of these items. Now, what does this Xi is 0? What do you understand? Uh, if I say Xi is 0, yes, anyone? It's null. That means I'm not taking any item. So Xi is 0 means this will imply ith item is not taken. And what does this Xi equal to 1 mean? Ith item is fully taken. So now you understand, I think, why do I call the previous problem as 0, 1 knapsack problem? Is this clear now? So earlier, what was the condition? Either I can take that item or not take that item. Those are the two options we had. And that actually corresponds to that Xi is 0 or Xi is 1. Okay. So this time in the fractional knapsack problem, I have to report for each of these items what fraction I'm choosing in my solution. So I have to output x1, x2, xn such that something happens, or what should I type with in the same line? Some subset of items. Here I have written some subsets of item with maximum possible value of something, right? With maximal possible value of some quantity. Which quantity would you like to maximize? So obviously this is not the case. All the items that are there in the knapsack, I'm not going to take the complete value of those items. Note that now we don't have the complete item with us in the knapsack. It can be some fraction of it. So what is the quantity that I should maximize then? So if I am taking xi fraction of the ith item, then what is the contribution of that portion to the value of the knapsack? So I have this ith item. So let me write it here. Ith item. I'm taking its value is vi, but I'm not taking the whole vi, but I am taking some xi fraction of it. Let's say xi is 0.2. Some fraction of it I'm choosing. Then what is the contribution of this xi portion of the ith item to the value of the knapsack? Yes. No, xi is just a fraction. So let's say, for example, uh, so ith item, I have, let me take a concrete example. So, mm 10 liters of some oil, and its cost is around 1,000. That's the value. This is SI, size of that item, and this is VI. So I am saying that I'm not taking the whole 10 liters of the item in my knapsack. Rather, I'm saying I'm just taking zero point 0.2, like this fraction of the ith item. That means what? What amount I'm taking? This actually tells that I'm choosing how much of that item. 2 liters, right? 2 liters of, yes. So it's item size is now 2 liters. And what is its corresponding contribution to the value? Value will be again xi times vi. That's what is it? Okay. So you got it. So now can you tell me out of this example, can you tell me what is the quantity? What should I write here? Um, Let me just think about that. What is the quantity that I am trying to maximize? I'm trying to maximize. So for ith item, I have taken xi fraction. That is the total value of the ith item, right? And for each of these item, I'm choosing what is the contribution to the value. I'm trying to get some vector x1, x2, xn where this is maximum, right? Not only that, I have to keep also the capacity constraint. And similarly, subject to the condition that whatever I'm choosing in my, I'm choosing xi here, I'm choosing xi. What's the size of this fraction? Xi times si. And this is the total size that I have chosen. That should not be more than the capacity of this. Okay. So see again here it's something similar to what we did before. Right? Here the items that I'm choosing, those are also contributing the whole thing, VI. Right? But now we can take some fraction of it, and I have to therefore multiply that fraction with Vi, and that will indicate the contribution of that Xi fraction to the value, right? And I have to do it for every item. That is the quantity that I'm trying to maximize. And again, similarly, we have this capacity constraint. What's the total fraction of items I'm choosing out of all of those n items? What is the amount that I'm choosing in my knapsack? And that should not exceed the total capacity, right? I hope this is clear. Can you tell me which one is the more general one? So is it 0, 1 knapsack or the fractional knapsack? Fractional knapsack is the most zero one. So if I, with this fractional knapsack, if I put the condition that in this fractional knapsack, I have this constraint, right? So Xi's are between 0 and 1. It can take any value between 0 and 1. If I restrict that, that either Xi is going to take either 0 or 1, then that's basically the 0, 1 knapsack problem. Okay. Okay, fine. So although this is a more generalized version of the 0, 1 knapsack, it's actually the solution process would be fairly intuitive, what we should say. So what I do, let me again go back to the same example that is this one. Okay, so this is the same example that we had before. So now this, and if you recall for 0, 1 knapsack, what was the solution? 0, 1 was the solution. Solution was by choosing item 3 and item 4. So the value of the knapsack was 8. That was the maximum that it. Can you guess what would be the solution now if I'm allowed to have uh, something even some fraction of the items, even if I can take. So your solution will be lesser. Uh, I'm saying like fractional knapsack will have solution value less than 8. Let's understand that. So can I have the solution of the fractional knapsack is less than the 0, 1 knapsack? Why? Actually, this is not the case, not true. So fractional knapsack will always have greater value because as you just said, 0, 1 knapsack is a special case of the fractional knapsack. Whatever solution that you have for 0, 1 knapsack, that is also a solution of the fractional knapsack as well. So for example, what is the solution of this? So in 0, 1 knapsack, I3, I4, that's the solution. Right? How can I write the same solution in terms of the fractional knapsack problem? I should say these xi, so there should be 4 values, x1, x2, x3, and x4. Right? So I'm taking x3 and so item 3 and item 4. That says these should be 1 and other things should be 0. Right? That is how I can write a solution of 0 and 1 knapsack problem in terms of fractional knapsack problem. So this is the vector x and c. Right? Understand? Yes. And what is the value of this? Value of this is 8. Right? So solution of 0, 1 knapsack is always a solution of the fractional knapsack. So whatever value that you get for the 0, 1 knapsack, that should be at least, I mean, it cannot be more than the solution of the fractional knapsack. In fractional, you can still add something. So that is what is happening in here. So what is happening in here, that what is the total capacity of the knapsack at this point? So capacity of the knapsack is 6 unit. But have we filled the whole 6 unit of it? So my capacity of this knapsack is 6 unit, but I have filled so far 5 unit of it. Right? But there's still an option of taking 1 unit of it. Now I can take some fraction, still I can take some fraction of item 1 and item 2. Okay. Now which one would you like to prefer? So whatever, so I have taken the whole item 3. Item 3 means that I have taken 2 amount of it. I have taken 3 amount of it. This value of this is 4. This value is again 4. And still I'm left with 1 unit. 1 unit of which item would you like to choose? And if you understand that, that will tell you what the algorithm should be. So you'd like to take the first item. So for 1 unit of what is the value of 1 unit of the first item? Can you tell me? What is the value of the first unit? Of 1 unit of the first item. So for item 1, 4 unit cost 3 rupees. Yes. So 1 unit will cost 3 by 4. what is the value of 1 unit of the second item, I2? It's 2/3. So which one would you prefer? This is like 0.75. This is 0.66. Which one would you prefer? So the item, I'd like to take the item which has higher per unit value. Okay, so I'm going to fill this remaining portion of 1 unit of the so this is item 3. This I'll take. This is item 3. This is item 4. This is uh, 3/4 fraction of item 1. So what is the value of this? This portion is 0.75. Right? So this is a solution. How should I express in terms of this vector? Vector will be 0.75 of this first item, 0 for the second item, 1 for the third item, and again another 1 for the first item. So what's the value of this? Value of this, whatever we had earlier, so 8.75. See, the value of this is greater than the value of 0 1 x. Okay, so this actually tells you a strategy of choosing the items. Which item? So suppose that we are at the initial stage when I've not taken any item in my knapsack. Okay, so it's complete knapsack is empty. I can take any of the items. Now at the initial stage, which item would you like to choose? Initially, we'd like to choose the item whose per unit value is maximum, right? So I will get the items first arranged in the maximum per unit value according to the per unit value. I'll arrange those items and I look into each of these items and I'll see whether I can take full amount of that item or not. And if I'm able to, if my capacity of the knapsack allows me to take the full item, I'll take that. Okay. And if it doesn't allow me, then I have to take some fraction of that item, whatever my already chosen. So whatever the remaining capacity we will take some fraction of that item according to that remaining capacity. Okay, so you understand. So let me again tell you what I'm doing here. So I have these inputs, right? Now what I do, I will arrange them in per unit value. So which one is having per unit value? So what's the per unit value of this? This is 0.75. This one is 0.66. This is 2. This is 1.6. Right. So I'll arrange them per unit value. So I take maybe so item 3. It has two. This is value per unit. Per unit size. So then I have item 4. Its value per unit is 1.33. Then I have item 1. Its value is 0.75. Then I have item 2. Its value is 0.66. So I'll arrange them in this order. Okay. And then I'll go to each of this list, each of these items based on this ordering. And initially my capacity is 6. Right? Now I have how much amount of this third item do I have? 2 unit. So can I take the whole 2 unit of those items? Right? So of course, yes. So I will be taking the third item completely with x3 to be 1. So after doing this, after choosing this, what is the remaining capacity? So capacity is now 4. Now I check whether I can take the next item, fourth item. So item 4 completely. Right? What is the size of the total size of the fourth item? It's from this table. I get it to be 3. So I can take that item completely. So I'll take fourth item and export will again be. So now what is the capacity then? Remaining capacity. That's 1. Now I can see that I cannot take, what's the next item? Item 1. I cannot take item 1 fully because item 1 has size 4. Item 1 has size 4, but only one unit, one size 1 I can take. Right? So I will be choosing just a fraction of the uh, just a fraction uh, of that item. And what fraction? It's whatever it allows us. Right? So in this case, I'll be choosing item 1, but not in full. I'll be choosing 3/4 fraction. Whatever fraction that I have there, I'll choose that. Oh, sorry, what? This is not the full, okay. I'm not choosing the 3/4 size. I'm choosing 1/4 of this. It's a 0.25 I'm choosing. Its contribution is it's not. It's 1/4 of this item I'm choosing. It's whatever the remaining capacity. It's basically the C by size of this. Okay. You got this idea? Okay. So so can we write the pseudocode? So what is the first step? arrange the items in decreasing order according to value per unit size. Okay. So I'm arranging them in the decreasing order. So I'll put the highest value item, most precious item first, then the second precious item. Let's say these are the ordering. So sigma is the ordering of this item. So I1, I2, IN. So this is not the input ordering. So after arranging the item in this way, suppose I'm taking this is the ordering that I have. So what should I do next? So it's again an iterative process. It's an iterative process. Okay. Uh, okay. What should I do? So I'll check the ith item. So I'll do it for each of these items. So uh, in general, suppose I have taken, so at some point I'm deciding whether to take ith item completely or some fraction I can take of the ith item. So if I see if the size of the ith item, so ith item in this ordering, I'm processing this in this ordering. So if I see the ith item is less than the capacity, what does that imply? Then xi is, what does that mean? The whole size of the ith item is less than the capacity. Then, so we are somewhere in these situations. So what should I do? Xi should be 1. Right. So value can be taken 1, but I will not care about the value at this point. I'll only set the value of the fraction that we are choosing. Xi is 1. I can, that means like I'm choosing the uh, complete item, and once I am choosing the whole item, its contribution to the value will be like whatever the VI is there. Value can be chosen as a whole, right? Else, if I'm not allowed to take the whole thing, then what should I do? What should I set the value of xi? So I am allowed to take C unit of it, but I have size more than that. So else means that is basically, although we generally don't write, but in this case, SI is more than C. Right? So then what is the fraction that you want to take? It's C by SI. Okay. And you're going to take that fraction of it. Okay. Since I'm saying it's an iterative process, I have to do something else also. If you are taking the 1 unit of this item, the whole item you are taking, then what is the value of the items that you have? So whatever value that you have gathered, you add VI to it. Okay. And what will be the remaining capacity? Capacity, whatever you had earlier capacity minus SI. Okay. But in this case, so when you are setting this some fraction of it, what would be the value of this? Value of this will be this xi times whatever xi that you have said, xi times vi, right? Okay. And can you tell me what would be the C now? So if I choose some fraction of the item, what would be the C value of C now? Yes. So C will be C minus this whatever capital. So xi times ci, it's like xi times si. Right? What is xi times si? Xi is, this is C minus xi is C by si into si, 0. Right? Then this C is always going to be 0. And then you don't have to do this, don't repeat these things anymore. You understand this? Okay. So, oh, you didn't get, because so what is the, this is almost the last step, that last item that we are allowed to add. So we see that the most precious item, whatever the items left available to us, I'm looking at the most precious item and I'm not allowed to take the full item. So what am I doing? I'm choosing as much as I can, right? So that says that after I choose some fraction of that item, this is my capacity. It's the knapsack capacity is actually full. Knapsack is full, right? So how many times should I do it? So if I see this, my capacity of the knapsack has something non-zero value, I'll keep doing this. And what should I return? The value that I have at this point, that I'm going to return to. Okay. You understand this now? Yes. Any question? Okay. So can you tell me one answer? So let me put one question. So this vector, whatever you get as a solution, can you tell me how does this vector look like? Suppose these items are in this order, x1, x2. So highest item. So first position, I have the item whose value is maximum. Value per unit size, that's maximum. Second item, value per unit size is maximum, like this. So can you tell me how does this look like? For the first item, either I'm taking some fraction of it or the whole item. Suppose I'm taking some fraction of this first item, let's say 0.7 fraction I'm choosing. Can I take the second item? Any fraction of the second item can I choose? Can I choose any fraction of the second item? No, because my capacity, why I am choosing some fraction of the most precious item, because that is the capacity. If I choose something more than that, I will be exceeding the capacity of the knapsack. If the first thing is some fraction, then everything else has to be zero. I'm not choosing anything else. Do you get this point? Suppose I'm choosing the first item completely, second item completely, but the third item I'm choosing some fraction of it. Then that also means that if from everything else I'm taking nothing, right? The solution should look like this, right? So it's a bunch of 1 followed by some fraction, some xi, and then everything should be 0. Remember that this ordering of these items, I have arranged them maximum, like in a decreasing order of the value per size. Okay. But after one fraction, there may be another fraction. Uh, yes, there may be. But what we are doing here in the code, if you see, that's why I have highlighted this point. Whenever you are choosing some fraction, it actually guarantees that your remaining capacity becomes 0. And once you have your remaining capacity to be 0, you are not doing anything else. Yes, what if capacity still exists? That will not be the case. Whenever we are choosing some fraction, what fraction we are choosing? As much as we can. That is the amount we are choosing. And once you do that, your remaining capacity becomes 0. Is this point clear? Okay, fine. So that's the whole process. And this is, we are applying here some strategy, something called greedy. At each point, at each choice of item, we are being greedy, right? We're trying to maximize our value. So I'm looking at the items, and whichever is having the maximum value per size, I'm choosing that item as much as I can. Okay, so I'll highlight more features of this greedy technique once we do further examples. But for uh, for now, this is the problem, and you should understand what's going on in this. And also, I try to point out the main differences between this 0, 1 and the fractional that you also have to understand. Okay, any questions? Okay, fine. Okay, fine. So as I said, so next Tuesday I'll not take the class, and I'll make sure that I'll take uh, extra class for those that I have missed out. Uh, okay, fine. Thank you. Thank you.